Hello everyone, this is Leo. Today I want to talk about in-context learning, which is a new paradigm for training large language models. And this paper explains the mechanism behind in-context learning from the perspective of information flow. So what is in-context learning? Is learning without updates. It's very simple. For example, I want ChatGPT to help me do a review sentiment classification test. In the prompt, I can give it some examples. For example, the input is a review and the output is a sentiment, the positive or negative. These demonstrations are the context. And based on those contexts, I wanted to classify this review. This is the final test. It can just output based on my demonstrations. And here is another example. I give ChatGPT a date. It seems confused why I just gave it a date. But if I give it some demonstrations, the input is the date, the output is another format of the date. It immediately understand what I want to do, so it can output what I desire based on my demonstrations, based on my context. This is very popular in the large language model community, but the mechanism behind this in-context learning remain underexplored. So the paper proposes two hypotheses. The first is that in the shallow layers of transformers in the large language models, the demonstration words, like the review part, will the information in those demonstration words will be aggregated into the label words. The label words is the label of the task. You can imagine that all the information from the input will be aggregated into the output. And this is what's the mechanism, this is the process in the cell layers. And in the deeper layers, the label position they have aggregated a lot of semantic information from the downstream words, and they will be further aggregated to form the final prediction. That is the target position. The information flow will be passed to the to the target position. And those two hypotheses are motivated by silence score. And the silent technique is a very common interpretation tool. It's employed to interpret the token interactions. We can see that the silent score is based on the attention matrix. The AHL is the value of the attention matrix of the H attention height in the else layer, and X is the input, and Lis is the loss function of the task. For example, the cross entropy objective for a classification problem. And we average all the attention heights to obtain the saliency matrix IL for the ILC layer. IL is a matrix, so ILIG represents the significance of the information flow from the GIS word to the S word for the in-context learning. I think don't make things so complex. You can just imagine IL is just another form of attention. It just so you can imagine the information flow is just another form of attention. That's what I'm thinking about. Okay, to further examine the phenomenon of information flow, the paper proposes another three metrics. The first one is SWP. It computes the average significance of information flow from the demonstration words to the label words. To compute this, we can compute the information flow from the demonstration words, the label words, and average all those information flow and to get the SWP. The other is SPQ, and is computes the average significance of information flow from the label words to the target position. The target position is the position where we form the final prediction. So to compute this, we should compute the label word, the information flow from the label words to the target position, and average them. The final metric is SWW. In the first two metrics, we compute the information flow from the demonstration words to the label words, and from the label words to the target position. But the interaction between demonstration words, those demonstration words are neglected. So we compute all the information flow between all those words, but we will exclude SWP and SPQ. That means we exclude the impact of label words, of those label words in SWW. Because SWP and SPQ are all based on label words. Okay, here are two experiments based on the three metrics. They are based on two different data sets. We can just look at the left one. You can see that the x-axis is layer and the y-axis is S value. In the shallow layers, we can see that SWP is much higher than SPQ, which means in the shallow layers, the main function is the information flow from the demonstration words to the label words, and as it goes deeper, SPQ is much higher than SWP, which means in the deeper layers, the information flow will transfer from label word to target position. So this proves the assumption. And in journal, you can see that SWP and SPQ is higher than SWW. As I mentioned before, SWW includes the impact of label words. So this also demonstrates the interactions involving label words will be very significant. Okay, we need further proof. So the assumption of paper is that information aggregation in context learning relies on the information flow from the demonstrations to the label words in the shallow layers. So to further validate this assumption, we need to block the information flow from the demonstration words to label words to see what will happen before and after. So to block this flow, that means we should block the attention. We can just set AIPI to 0. You can remember that P is the position of label word and I is the preceding word. That means demonstration words. So for that column of the attention matrix was set all 0. In that case, label words cannot access information from the prior demonstration words. And to qualify this process, the paper provides two metrics. The first one is the label loyalty, the second one is the word loyalty. So we can just think they are all loyalty. They are used to measure the similarity of the output before and after blocking the information flow. In the experiment is based on two different models, so we can just look at the first one because they have the same trend. The dotted line shows it as 100% loyalty. It means the output before and after blocking the information flow is the same. Firstly, we should look at the blue one and the orange one. The blue one is blocking the information flow as the first 5 layers. The orange one is blocking the information flow as the last 5 layers. So we can see that if we block the shallow layers information flow, it will significantly change the output because the similarity is pretty low. But if we randomly change it, we don't change, oh, randomly change the word. We don't block the label words information flow. It will be not that significant. So that's also proves the significancy of label words and also the shallow layers function. Okay, to further prove the function of deep layers, we should examine the correlation between the information flow from label word to target position and the model prediction. So the model employed AUC-ROC score to quantify the correlation between ALQPI. You can remember that Q is the target position, is the position of final prediction, and the PI are the label words. So this is the information flow from the all the label word to the target position, and the final prediction for the else layer. So we use AUCR score to quantify the correlation, and also to quantify the cumulative contribution. The RO is used to quantify the accumulated contribution. So we can see that at the shallow layers, the AUC ROC score is nearly 0.5. As what we learned from 520 last semester, this value is meaningless. It shows no correlation, but as the layers go deeper, we can see that the AUCR score almost achieve 0.8. It shows a strong correlation, and as it goes deeper, the accumulated effect is going higher. So I think that's that's clearly proof that the information flow process from the label word to the target position, they result in the final prediction. Thank you guys. That's my ideas. If you have any questions or about experiments, about equations, about concepts, please free to contact me. Thank you.